Okay, so hello everyone, and especially Varun. Thanks for being here and taking the initiatives. So, without further ado, we'll start our session today. So, last time we were okay. So, I'm sharing my screen. Yeah, is it visible? My screen. Varun, is my screen visible? Hello, can you see my screen?
Hello.
Yes, Varun, is my screen visible?
Yes, visible. Sorry, my laptop just ran out of battery, so I had to go and restart.
Yeah, I was waiting for this. Okay. Why every time my face is, yeah, it should be here. Hide we switch camera, no. Spotlight.
Patience.
Okay. So yeah, so last in our last session, so we have done this. Yeah. So we have done the basic of fluid dynamics for astrophysics, the macroscopic, microscopic quantity. Just a recap, and then we go to the continuum limit when it will hold good or when it's not. So it's a very important phenomenon that the number of particles in that system should be very large to consider that a continuum. hence as a fluid. So, and then we head on to the difference of fluids with solids and gas, and fluids streamlines and how the streamline vector is defined and all. So yeah, those are the basics and the basic property of streamlines. The other properties, other feasible properties of displacement, that infinitesimal displacement is parallel to the velocity field. It's kind of obvious because we do, that's how we define the velocity. Properties of stream functions and its interactions with the stream vector and the velocity of the fluid, those things. And then yeah, we have gone through some assignment problems and we have solved that together. And then yeah, so that's all. So I haven't seen any posted questions on the community group. So I hope that everyone have understood the topics and the questions very well. If not, you can still post your questions in the community group. I will try to answer those as much as possible. So yeah, that's the things for last week. Hmm. So for this week, so we'll start. Okay. So yeah. Hmm. So for this week, I can't find my Bluetooth mouse. Otherwise, laser pointer. So yeah, I think now you can see the pointer, na? It will be better that now you can see that where I am pointing and all.
Right, right, right.
Okay. Anything about this screen you can do? Can we make it full screen or something? When I'm sharing, they are not letting me do annotations restarting on film. What is happening? Yeah. Okay. Now again, laser pointer is not working properly. What is happening? Okay, wait. Use of this app will not be recorded. What? What does it mean? Cola, current. Ah, yes.
Was you saying something? I was unable to hear you for the past couple of minutes.
Wait, wait. I think I have downloaded the file. I'm looking just looking the file. Share icon, but no. Quick to is not download. Sure, it can be downloaded right now. Okay. I think you can see the screen, no?
Yes.
Uh, wait. Okay. So I think it is enough. I'm just saying that how much of my skin is coming. Yes. So it is coming there. So okay. It's okay now. You can see my skin now.
Yes. I can.
Okay. So today we'll start our session 2, and we will start about the conservation equations. Okay. So as it written here that any quantity for conservation, we think like any quantity for particles. So what are the intrinsic quantities of the particles? So there are few, like mass is an intrinsic property. Okay. There is charge, there is momentum, and spin. If you consider spin is also there. So these are some intrinsic quantities for any particle. Normally a particle, we are talking about particles here, not waves, because we are dealing with fluid particle. So only particle nature will be shown here. So if any quantity of it is conserved, then the change of this quantity in a specific volume V implies that it is a influx or outflux of A through surface S of V. So then we can calculate its influx or outflux. Basically, it's flux through a surface V. So you can see that how much of it is incoming or going from the system. Okay, is it incoming to the system or outgoing from the system? So the quantity we can define that. Can you see my cursor? You
Yes, I can.
can see my cursor, no?
Yep.
Now they are not giving the annotate option. Side by side is not looking good. Yeah, reporter, I think it is looking good. What is optimize? Share sound. Give control. What is optimize? No need of optimize. Annotate option is not anymore there. Anyway, I can't write here on my lappy. So I think it is good now. Right. So okay. So yes, so the conservation equations. Is better in that way. Okay. So the conservation equations. So the influx or outflux of A through surface S of V. So I would tell that, okay, tell me what will be the, but I'll tell you for this time that the flux of A. So okay, so flux of A, that will be rho times U. So that quantity rho is basically the density. Okay, rho is basically the density, and it is defined as, okay. Here we're talking about basically mass, but mass per unit volume, because the whole system will have mass. So we are talking unit volume mass. That is the intrinsic property rho. So the flux of A will be rho times the velocity vector U. So that's how it is defined. That the rho U, it is A over area minus time. So and yeah, this is the, where it is. Okay. Yeah. And this is the Gauss divergence law, right? You must have studied that in your math papers. Yeah, math subject in your common general paper or something. This is the Gauss divergence law. So yeah,
Yeah, yeah.
you know it, right? So
Yes, I do know. By the way, the screen is a little small. I mean, it's not completely readable.
screen is small.
Yes, I mean, the kind of setup that I am able to see, uh, your your camera is way bigger than the screen you shared.
Actually, you can only see me alongside the screen, right?
Yes, I can see you as well as the screen, but you are looking way bigger than the screen and it's not completely readable.
Okay, okay. So I understand. I think it's about how I am presenting. Layout, content only. Now can you see?
Yes. Okay.
Now I think it is bigger, no?
Yes, yes.
Okay,
Absolutely.
understood. I mean, where I am presenting, na, so I can see the full screen, but it was like for you. Okay, anyway. So yeah. So we will keep this format only. Okay. And
Thanks.
the ledger point used worked that time, but now it is not working. So, don't know what happens to this. Okay, anyway. Yeah, it is not removing. Then there is no point in. Okay. So due to that, so we get the del t of the integration of this factor as minus of integration of rho u dot ds. So where use the velocity vector, as you can see. So that can be in any direction, but s is the no, surface direction. Surface direction is normal to the surface. It is always normal to the surface. It is denoted as s vector. So normally you can think that the surface has the direction as n hat. So then we get this as a conservation equations. So then we'll get, if we if we apply the Gauss divergence theorem. Okay. Oh, sorry. I mean, yeah. Before that, I will go. So okay, I will try to explain this uh, analytically. Okay. So suppose, so this is a system, right? The density is rho, and that is mass per unit volume, and volume is V. Okay. So suppose that there is continuous flow of mass. I mean, inward or outward the system. Okay. Suppose in this case it is outward the system. I mean, particles are flowing outside, so uh, it is emitting the system. So what is the mass loss? If you consider the mass loss, so mass, the small mass as at a dv volume, that will be rho times dv, right? So rho times dv is the mass for a infinitesimal uh, infinitesimal portion. Okay. So, and that is dm, basically dm. So the mass loss is dm over dt, right? So mass loss is dm over dt, that is this term del t of rho dv. So that is the mass loss, and this is the one way we can represent. Another way we can represent by the flux. So the flux of is this rho times u. So u is the velocity vector. So we, as we already explained, that uh, flux is rho times u. This is the flux. That flux means how much of it is incoming or outgoing. So negative because now it is emitting the system. So mass is losing. So that's why the negative sign is given. So rho times u is the flux, and it is over the area ds. So rho u dot ds. So dm will be rho u dot ds. But for overall, for the whole volume, if we consider the whole volume, then we need to integrate it, and upon integration we will get this. And then we apply the Gauss divergence theorem. That is from this rho u dot ds. It will be uh, del dot rho u del dot rho u, and del dot rho u basically that is scalar. So del dot rho u dv. So dv cancel out, integration is also cancel out. So only del dot rho u will be there. So this is conservation of mass in Eulerian frame. Okay. This is called Eulerian frame because we are not taking any Lagrangian or Lorentzian frame. Okay, we are not taking relativity or anything else into consideration. This is normal. I mean, what you normally go through. So that frame, that is Eulerian frame. So I know you all know, but still I am just making you revise and explaining some little bit things. So this is the conservation of mass. So then. So from that, then we will get in the next step if we, uh, yeah. So this is the partial derivative of del dot del t, right? So del dot del t, and if we do the total derivative of rho with respect to time. So time total derivative is, one is partial derivative with time, another is partial derivative with the space. Okay, and with the space it will come as this, right? That del dot del t, here you can do, I mean, both side you can do. Another thing you can do that you can exploit this. You can del dot rho u. So if you take the rho outside, then it will be rho times del dot u, right? Because rho is scalar. Remember, rho is scalar, u is vector. So rho times del dot u. Another time will come as what? That you check the u outside, so u dot grad rho. Okay, so you can take this side or this side, anywhere you can do. In anywhere you will reach here, that it will be equal to minus rho del dot u. Okay, I'll give you a little homework to do this by your hand. It's just a 1 to 2 line step. It just tell about how we take that del dot, two thing, del dot ab. Okay, but here on is scalar and is vector. So it's just the vector compartmentalization. So you'll get this. So we are we are getting the d dt of rho is minus rho del dot u. Okay, so this is called Lagrangian frame. Okay, so and the difference is this is called Eulerian frame because we are taking only the partial derivative of time, right? So we are thinking that we are fixed in space. So think like a rotating system. Okay, so if a rotating system fixed in space means we are in the rotating frame. So the frame itself is rotating with the rotation of the system. So in space it is fixed. Only the time derivative is into consideration. But for Lagrangian frame, we take the total derivative. I mean, we take the total derivative, that how rho changes with time as well as space. So it is not fixed in space. So it's called Lagrangian frame. So the two frame you can think, the Lagrangian frame is del rho del t and Lagrangian frame is d rho dt. Okay. So these are two differences between them. Equation of continuity. Okay. So yeah. So for flow speed of fluid. Okay. So then we can reach there. Um, del dot u. Where is del dot u? Yeah, del dot u is here, na? Lagrangian frame. Del dot u. So suppose the fluid speed is much less than the sound speed. Okay, sound speed, sound speed we can calculate from the temperature and all. basically velocity for microscale is velocity. For on each particle velocity u, we take the average velocity or like yeah. So then we get the sound speed in fluid. So if the flow speed is very less than the sound speed, it is called incompressible flow. Basically, basically it means that the fluid speed is not that much. Okay. So it is so how we get the sound. So actually what happened? So like I am talking. So when I am speaking with my vocal cords, okay, the sound is generated there, and as I am speaking through my lips, so the force is acting on the uh, air here, okay. So air molecules. So I mean, largely you can consider that as a liquid thing also, because you know that uh, sound follows higher speed on liquid than gas and much higher in solid than liquid and gas. Okay. So as we speaking, so I am I'm pressing the air. Okay. So and then the air molecules here vibrate. They transfer the energy to the next column of the air. So that's how it is propagating. So basically, the sound speed has the relation with the flow speed. Okay, flow speed. So now suppose, so it is flowing now. So now suppose this flow itself is, comparable to the sound speed. So as we are talking, because it is also moving very fast, so the fluid will act as a compressible one. So it will look like this rubber kind thing, like for mercury. So mercury, is compressible. So it will like compress, it will like shrink, or it will like enlarge. Okay. But when the flow speed is very less, I mean, it's like the fluid is relatively very much in constant state. Only the sound is flowing. Okay. So then we can consider that as incompressible fluid. And for incompressible fluid, the del dot u is zero. So basically the same thing, that the flow speed is very less. So the overall displacement, okay, positional displacement of the velocity will be zero, because the fluid is incompressible. So then del dot u is zero. So now if we put del dot u is zero here, we will get what? Okay. So if del dot u is zero, we will get from here that d rho dt is zero, right? That means rho is constant. So basically we're hinting to the rho is equal to constant thing. So in compressible fluid, so rho remains constant. This rho, as how system is flowing outside inside, so there will be the density will be constant. Okay, mass can uh, yes, mass can change, but the density remains constant. So that is for incompressible fluid. Okay, this is the one thing, and then the next thing is then conservation of momentum. So for momentum, we know the momentum is just basically mass times velocity, mu, but we are talking about mass per unit volume. So we'll talk about rho. So rho times u. Yeah, so this is momentum density, rho times u. We're talking, we are giving a term density because basically it's just per unit volume. That's why density. Because we know density is per unit volume. Okay. And so the momentum flux will be this term times the velocity vector u, because that's how we define the flux here. Remember, that's how we define the flux. So we define the flux here, that it will be the term times the u vector. So the momentum flux, and then similarly the change in momentum in volume v. Okay, so you will think that earlier we have done what? Earlier we have done that the change of mass in the volume dv is del delta of rho dv. So you will think that for momentum also it will be like rho u times dv, right? But it is not. Okay, it is not. It is actually this rho u, because this is the momentum flux, right? Rho u times u. Okay. I think there is some typo. It will be actually same. No, so it will be actually minus, equal to minus. It will be not question. It will be equal to minus. This is a typo. The laser is not working. Okay. So in similar manner, okay. Obviously, in the ds term, it will be u dot ds. So actually, it will be the same in same format. What? I have done that, no? Okay, my bad. So anyway, you understand the part that. So similarly, it will be like this for the momentum also. It is omitted automatically. I think it is not working that way. So then, if it is equal to minus, so we take that term, and if we like break it further, okay, the change in momentum in volume v is intrinsic change plus the influx outflux through s. So del T of this, and if I break this term, so we'll get from the Gauss divergence theorem that it will be del dot rho u times u dv, and then the whole term will be like this del T, because this had dv, this had dv, this whole term is like this. And then we take the what is the forces acting on the fluid. So there will be one body force that will be due to the mass or weight of the fluid, and there is the force on surface. So the surface acting force, that is denoted by F surface. This is basically the force. We are breaking the force as two parts so that we can compare this. And the body force is due to weight, so it is rho g times dv. So rho g is the weight of the fluid, okay, per unit volume, and surface force is due to the pressure, so p times area. So simply you can think that there is a pressure time area, that is the force, right? So don't don't worry about this p I j term. This is just a tensor form. I don't know whether you have dealt with tensors or not. So tensor are basically the next level to the vector. So like the first there comes first the scalar, which are the rank 0. Then comes rank 1, that is vector. So scalar is only one term, so that's why we call it as a value. Okay, because on a single term. Vector, we know that it is like three terms are there. Okay, in 3D. So like for velocity, ux, uy, uz. So it is a matrix. You can think of matrix. It is a 1 by 3 matrix. Similarly, for rank 2, we'll get a 3 by 3 cross matrix, and that is called tensor. In general, everything is tensor. That is called rank 2 tensor. So that's how it is calculated, the surface force. Okay. So then then we compartmentalize the this term as pressure as del P del X times dV. Okay. In a similar fashion that we have done earlier for area and for dv. So it basically del dot p dot dv. Okay, because p dot ds is there. So it's same again, the Gauss divergence law. And then we are reaching to the term, and then it will be like del dot p dv. So you can take as much analogy as you want. You can analyze that, okay, pressure is acting as a unit change of the position with the volume. So you will just reach there. So that basically the tension analysis. I don't go much deeper in that. So okay, so we get this term then. So this is at dv, this is at dv. Okay, you see the similarity where you are going. So now if we add it, this term, if you just omit the dv, so what will be del t of rho u plus del dot rho u is equal to rho g times del dot p, right? So we'll come there. So this is the conservation of momentum equation. Okay. So from here, if we simplify it, it is already simplified. So it is the Eulerian equation because we have del t, the partial derivative with time, the total one. So that's why it is in Eulerian frame. So Euler equation. It is called the Euler equation, or you talk the flux, momentum flux. The mass flux is also there, and gravity g is playing role, and the pressure is also playing role here. Okay, so and we know we previously have done for the mass conservation del delta of rho u, so we can use this. This is just first doing partial derivative. Yeah, partial derivative of this. So we'll reach there. Okay, the two term will come, and then we do yeah, using the mass conservation equation, the continuity equation, we'll get this for the first term minus u grad dot rho u. If you remember the first term, second term is a similar simple like this, and then we can break this. Okay, I will spend a moment here. You see the page, see the equation, and tell me what you don't understand in that equation. I think that will be much better.
Hmm. Yeah, because it was pretty.
Hmm? Sorry,
Uh,
Varun, I can't hear you. Yeah,
yeah, I just said that that's fine, and I got this one.
you
It's
got
clear.
na?
Yes.
Okay, good. So you have read up on the tensors and all in your.
Yeah, outside coursework, I have read about the basics, not much, but I know the basics.
So you know the basics of tensors like covariant, contravariant, and all, or how the derivatives are done.
Yeah, right. Only up to that much.
Okay, okay, good, good. So yeah, so I think yeah, then you can understood. You can understand that. Okay, it's basically the same thing, just the partial derivative, nothing else,
Mhm. Right.
right? Because you are taking the u outside, then you have to use like uh dummy index. Okay, otherwise you can't just use ui. You have to use different uj. That is general. Obviously, there will terms come when I and j both are equal. That will be like ui square. Other terms where they are not equal. So okay, so that's one thing. Then we get from this term this. So and then again, yeah. So then we can use for this uh, this equations, and after the derivation, I will share the PDF. Don't worry, and then we'll reach here. Okay, you just don't worry about these terms. Okay, will be simplified. It's just the intermediate journey. Okay. I think yeah. So so then it is said that for inviscid fluid, okay. So inviscid fluid means viscosity. So we are not dealing with viscosity right now, okay. We are neglecting the viscous term because if we consider the viscous term, the eta term will come here. But now we are not dealing with viscous fluids, okay. That is viscid fluids or viscous fluids. So inviscid fluid means where we are not considering the viscosity. So if we don't consider the viscosity, then only the diagonal terms will be affected for the pressure. That is basically the pressure will be then scalar. Okay, it's like uniform pressure everywhere because there is no viscosity. Okay, and the system is a, I mean it's a bound system, so it will be moving. So P Pij is equal to P means the P is scalar, the value of the pressure, and delta I. Delta I, you know, this is the Kronecker delta function. So delta Ij will be 1 when I is equal to J. Hence, when I is not equal to J, then it is 0. So basically, it will be scalar term. And then these terms again further breaking down will is there. And now we can simply write del P in Pij, del P. So then we head on to the, yeah, we head on to the final equation. That P del U del T plus rho times U dot grad U is equal to minus grad P, because this is simply minus del P del X, na? So minus grad P del Xi. Xi means all the three directions. If three directions are involved, so all the three directions X, Y, Z. So this is grad minus grad P plus rho G. So now it is in vector form. So again, if we do this Euler equation simplification, uh, anything else I have done in this page? Okay, this is the same. Okay, this is the same. Rho del U del T plus rho. Yeah. So yeah, the question is, can you tell me that whether it is valid for compressible flows or not?
Ideally, it should not be valid for compressible flows because earlier we had made the assumption that del dot U should be zero.
Huh?
I was saying that if I recall correctly, then earlier only we had made the assumption that del dot U should be zero, and so the flow should be incompressible.
Okay. One more thing. Last time I also uh, presented like this, na, in my laptop only, screen sharing.
Right.
Okay. So was the screen that I'm sharing was recorded? Let me check once. Was that recorded last time? Oh, it was recorded. Okay, good. I only use this mode, na, this content only mode, na, last time also. Huh?
Right. Yeah.
I don't use this kind of thing, na, stand out, or it is very small now. How is it now? The screen is good, or
Yeah, now the screen is good and most of the text is visible. In front of some of the text, your office is coming, but otherwise it's mostly visible.
oh, but I am coming now. Some of the text are hidden, right?
Yeah, exactly.
Because I am in front. Okay, but this is the best, right? You can see the whole thing.
Absolutely, that's the optimal way.
Okay, okay. So I think, yeah. So the screen is also captured in the recording. I can see. But the screen recording video and this one is a little different. Here I can see you and all, but when I recorded it, so anyway, I only recorded like this, now, so it shouldn't be a problem. Okay, okay. Yeah. So yeah, tell me. So what did you say? So should it be valid for compressible flows, or what do you think?
No, I don't think it should be valid because earlier all the sort of
It's 8
treatment we
o'clock.
did, or whatever treatment we did earlier, that kind of suggested that there was assumptions of incompressible, if I'm right.
But here we haven't taken any consideration that whether any compressible factor, right? We take the compressibility factor for the earlier on, for the mass conservation. Remember, for the
Mhm.
mass conservation, yeah, for the where too many slides. Yeah, for the mass conservation, for the incompressible flow here, for the mass conservation that I told you that it will be 0 dt is equal to 0. Here we haven't taken anything yet, but okay, you'll get your answer just in a bit. Hold on to it that whether it will be valid for compressible flows or not. Okay. So for incompressible fluid, we already get the result that d rho dt is 0, right? Because d rho dt is basically del dot u is 0 minus, there are minus, but okay, there's the, we're getting just the value. So it is 0, right? D rho dt is 0.
Right.
And for irrotational flows, we know that curl of u should be 0 because curl is the measurement of the rotation. So yeah, it should be 0, right?
Right.
Oh, I was looking for the mouse and the mouse is here actually. Okay. Sorry. Okay. 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 I think now you can see the laser pointer. It is much better. But the problem is when I am pointing to the laser, I can't, go through. Anyway, so for irrotational flows, we know that the curl of u will be 0. And for incommensurate flow, d rho dt is 0, right? So then from this term, okay, so then we'll head on to it. Okay. So okay. So then the rotational flow is 0. Okay. These are inviscid. So this is the fluid motion, just a random motion that ux. This is the direction of ux. This is the y direction. Okay. Irrotational flow implies inviscid flow. Okay. So irrotational flow. Okay. So I'm talking that basically when the fluid is not rotating, okay, only moving. So there won't be any collision, right, with the fluid, other fluid particles because they are just moving parallelly. Okay. So it is irrotational means it is a inviscid flow. So there is no viscosity. For ideal cases we are considering for this kind of viscose, not other kind of like this parallel layer viscosity. We are not talking about that. So can you tell me it vice versa is true? Okay, so first I think okay, I haven't written here. So I think I have partially answered for your question that is it valid for compressible flows? So obviously till now we haven't taken any consideration It is for in general, right? For in general fluid, we have taken only on consideration that it should be inviscid, right? We have taken the inviscid yeah, we have taken only the inviscid constant. That's why we are written grad p. But we haven't talked about the compressibility yet, no? See, we haven't talked about the compressibility yet.
Okay, okay.
Yeah, only the inviscid one. So that's why you are dealing with the inviscid things now. So then tell me, another question is, irrotational flow implies inviscid flow. Is the vice versa true? What do you think?
Mhm. There could be cases where the flow is rotational, but not necessarily inviscid. Like if I say, recalling from the last couple of lectures I saw from week 3, there were some examples where the fluid was going around a ball where there was Magnus effect. Although it involves viscosity, but still, if we think somehow there's a flow, then it could be rotational.
Yes, you're right. So I'm glad that you connected it correctly. So yeah, that's how you evolve, right? Okay, so yes, so I didn't expect that you will think okay, but that's good. Yeah, so you have seen already through examples, right? So yes, so that's it. Good. So then, so yeah, this is the constant that I have told already. Rotationality may be set by other forces. Okay, so yeah, so other forces can be involved there. And yes, you're right that vice versa not exact, not necessarily true, right?
Yes, yes.
Hmm, good. So then, in compressible flows, we get this irrotational flow. We get this if Karloff is zero, so you know you always can define
Mhm.
u as something at phi, like how we define potential, right? For gravity, when the force is conserved, curl of F is zero, then you define that F is minus of grad V, that is the potential. And where from where we reach to the potential energy and all. So obviously we can define U as grad phi because curl of grad will always be zero. Okay. I say always, but yeah, there is a catch. So that is a classical mechanics problem. That is it always zero, but or is the issue? But it's actually not always zero. There is some terms comes single what it's called uh, multipole or single pole. So those things come. So where it is it not obviously be zero every time. Okay, but for our system, for classical systems, so it is zero. So that's why we always define that U is of grad phi. Okay, and incompressible plus irrotational. So if we combine these two, okay, we'll get that what del square phi is zero. That is basically Laplace equation. Mm, okay. If you just put grad phi in place of here, okay, in place of u, you will say that curl of grad phi. And if you break it, so you will get two terms. So one terms will be del square phi, and the term will contain del dot u, and that you already know that is zero. So hence we reach to the del square phi zero. I will give you that as a homework. You can try to solve that and tell me next time how did you get. So you will get zero, but that is just basically vector compartmentalization. Just vector cross product. How it has been done for this. Uh, this grad vector, nabla. It's called nabla, na? Yeah, nabla operator. You know, right? That this is called nabla operator.
Yes.
Okay. Just name. I mean, different names are given. I'm just referring you that because different textbook can use different name for that. So one name is nabla operator, or yeah, we call it usually grad or del, right? So it doesn't matter. Phi is featureless because del square phi is 0. Here we have done some Taylor series expansion. Okay. I hope you know Taylor series expansion is what.
Yes, yes, I do.
Yeah. So yes. So Vx plus a. So we are doing around x term. So Vx plus this is the extra term. So a times dv dx plus a square by 2 factorial d2 of dx2 and those. And what is there? I think something is wrong there. This will be actually Vx minus a. Okay. Uh, this is actually Vx minus a. This is actually Vx minus a. Okay.
Okay.
Because you can
Mm.
see now that the first term will be minus a and then the minus of a square, that is again will be plus. So now,
Yeah.
yeah. So this is just we are just trying to do the average of uh, the potential V, like okay, like this. How can I say? Suppose, yeah, suppose, yeah. So this is one place, right? So suppose this is, I think its font is much bigger. So the Vx, and then this is the distance of A, the equal distance. This is the negative direction. So this is minus A. Okay. So the potential. Suppose you know the potential here, V x minus A, and this is V. This is a bad idea to writing like this. Okay, so thus the Vx will be the average of half of Vx plus A plus Vx minus A, right? That's how we normally usually do the averaging of like anything, right? That's how we average things. So yeah, it is the same thing, right? And we are ignoring the higher order terms. So again, for averaging, we do ignore the higher order terms. So you are ignoring this, and if you add this to this, and this will cancel out. So only half of the two Vx will be there. So yeah, it's pretty simple. This means order of a cube terms, like a cube higher order term. This is mean that higher order terms you are ignoring. Like there will become na a cube by 3 factorial, that is a cube by 6.
Mm-hmm.
Yeah, d3 v dx3 and all.
Right, right.
I think understand. So this is captured. Okay, and then phi featureless. Phi x is average of values of phi at point around x. So similarly, yeah. So phi is the average of values of phi at points around this. So suppose we get a system of here, I mean like this. Okay, this again come this side. Okay, anyway. So suppose we are getting that. Okay, phi this. We are getting different values around this point, and we are saying okay. Suppose I want to have the value at this point. Okay, you don't have the value there right now. Okay, you have the values all here, but not here. So then what you will do? You just average out things to get the value there, right? That's called uh, that's somewhere called interpolation. Okay, yeah. Interpolation is there. You will come across these terms if you do computational physics courses. So, or you may have already gone through these terms. Okay, and then that's why it's called phi is featureless. It's not that you have the exact value at that point. It can't be the near about values. That's what this the special uh, properties of this Laplace equation for phi. So recall for irrotational flow stream functions. If you remember how stream functions is defined for irrotational flows, that u is minus of grad, sorry, minus of curl of psi xy times z hat, right? This we have covered already in our session one. So if you remember, if you don't, go back to the earlier videos, you will see. So u is defined like this. So yeah, so you have this del square phi is 0 or this curl of u0. So now prove that psi also satisfies Laplace's equation. Can you solve this?
Mm, I might have to work around a bit because it's not exactly clear to me, but I might be able to solve.
You understand now what is the question, that psi
Mm,
satisfies Laplace equation. Basically, it will be
yes.
like this: del square psi is 0.
Mm, right, right.
So it's very simple. I mean, okay, if you just think about it, what is the properties? Where we have started curl of u, right? Curl of u0. So here u is here, right? U is here. So just do curl of this. You take curl of this side and then curl of this side. Then what will that be? Curl of psi, right? That is
Right.
basically a cross b cross c. A cross b
That will
cross c
be
vector, right?
right, right, right.
Yes. And what do you know about how we do normally a cross b cross c? Do you remember? Okay. Let me write here. I think I can. Array. I think I should remove this. Anyway, it won't come in the PDF, only in the background, so it doesn't matter to keep. So how we do? Array. Sorry.
It was A dot B times B minus A dot B times C.
Yeah. But remember where the bracket is, right?
Mm, right.
If the bracket is like this, right? It will change, na?
Mm.
With respect to
Yes,
the,
obviously, yes.
you will do this. You will take that b vector. We're not writing the vector sign because everything is vector here. A dot c minus c of a dot b, right? Right? Hello, Arun? Yeah, it is simple for normal
Yeah.
vector, but now if you are dealing with, you know, curl of this, then things get little messier. Okay? Things won't get that much simplified because several other terms will come, because grad vector considers
Mm.
several terms. So,
Right, right,
right?
right. Mm. gradient of a divergence and then later.
It always sound. Yeah. So yeah. So then, and it's homework, but I will give you some hint. See that call of view. So then call of psi z hat, and then we have break down this as minus of grad dot psi z. So basically again same thing, like this is b. So take b outside, a dot c del dot psi z, right? A dot c plus, now you will take c outside psi z, but you can't take c outside, remember, because these are operators. So yeah, c outside, but a dot b, right? So what is a dot b? So del dot del. Okay, so del square, and it can't be like psi z del square, right? Because del square is a is an operator. It has to operate on something. So del square would operate on that psi z. So it's basically the same thing that I explained. Yeah, only that because now it is the operator, so a dot b will come first and c will be, okay, c won't be here, c won't be here. So for this, c will be here, right? It is an operator, na? So difference between the vector and all is this is an operator. So it has to come before it. You can write that psi j del square, but then you have to give something after del square. Okay, because this and this means totally
Mhm.
different. Del square psi j, del square psi j. Okay, or
Yes, yes.
psi z hat and psi z hat, psi z hat del square. It's totally different thing. Okay, totally
Right.
different thing. It doesn't mean it doesn't. I mean, it is. I mean, it is like a operator. Okay, okay. Size disk itself is an operator. Disk is an operator. So we combine that with some value. Size disk, it itself is an operator. Okay. So del square is scalar actually. Del was vector, right? What is the value of the nabla operator? Del is uh, I hat del x plus j hat del y plus z hat del z, right? So that
Right.
was, yeah. So that is a vector, but del square is scalar because why? So now del square is del 2
Is it
del
the
x2 plus del 2 del y2 plus del 2 del
Mm-hmm.
z2, right?
Mm-hmm.
Yeah. So that is a scalar, and it has the direction of z hat. Now this. So overall, this is a vector. Okay. So again, we have made. I mean, like this, you can make another operator. Okay. Which direction is only one direction now, z hat. Okay. So like if you do any function alongside it, so yeah, it will follow this direction. But earlier, if I took only del, so del has its own directions, 3D directions. So yeah, so that's how it is different. So then you can see, okay, del square psi z 0, right? So del dot psi z, that is what? Del dot u, right? No, sorry.
Mm. Del dot say.
No, not u, sorry. Del dot. Okay, psi z is not u. Call of psi is u, right? So psi. So then what do you do? Uh, yeah, we take the del dot psi z. What is del dot psi z? Is del de. So yeah, see, del has the x hat, y hat, z hat, but it has only z hat. So only z hat terms will, survive. Other terms will be zero. So it will be like del z of psi. So del psi del z, right?
Yeah, the other terms would vanish. That I got it. But why is that? Why is this del by del z also zero?
This
I mean,
term. Okay, okay. You remember the stream functions? This is the
yeah,
properties of the stream functions we have defined, no?
okay, by definition. Mm-hmm.
Yeah, by definition, how stream, because psi is stream function, it comes from the velocity and all. So what is psi here? X and Y, na? See, this is
Mm-hmm.
how the stream function defined, na? Psi x y, and your derivative with respect to z.
Right, right, right.
In
Okay,
other
yeah,
words,
got
yeah,
it.
it has no, yeah, z component. It's a partial derivative, so it will be zero. So now if it is zero, so then del square psi z hat is zero. Basically, z hat is a non-zero vector. Okay, it's not a null vector. So obviously, del square psi should be zero. So hence proved. So del square psi is also uh, what is Eulerian Euler's, sorry, there is, yeah, Laplacian Laplace equation. Okay, it will follow the Laplace equation. So yeah. So any problem till now? So do you have any query?
No, yeah.
Okay, good. So then Euler, where we are going from here? It's a different slide. Euler equation. So this is the Euler equation again we have mentioned. This is the same earlier equation for the from the momentum conservation. Okay, we get this one, that rho del u del t plus rho u dot grad u. So try to understand the equation. It is saying this is the density, this is the velocity change with time. This is again the density. This is u dot grad. So again, u dot grad is an operator, right? Ux del del x plus ui del del y plus uz del del z. That is an operator, and it is operating on the velocity.
And you.
Yeah. So it's like a velocity field. You can think as a velocity field. Okay. We typically call these things as field because this is an operator acting on a vector, so it is creating its own field like that. And this term, this is grad p, this is just the pressure gradient. Okay, just the pressure gradient, how the pressure is
Mm.
changing over distance. And yeah, this is just the weight, the gravity, taking consideration the gravity g, because we take the body force, na, and body force is due to the weight of the fluid here. So this is the Eulerian equation for inviscid fluid. Remember inviscid fluid? That's why we are writing this as minus grad p, p as a scalar. Otherwise, we have to write the uh, pressure tensor Pij, and that will come across this diagonal term, and then off diagonal term that is written as pi, actually pi ij, but we are not dealing with that here yet. I don't know if any further course, or if any of you are interested, maybe we can discuss that. So this is the Eulerian equation. This is very important equation for fluid. Eulerian equation. You must have heard Euler equation. These are this is a very basic and very important equation for fluid dynamics. All three, like for momentum, for mass, for energy, all three are very important. This is for the momentum one. That is called continuity equation. This is the momentum one. So then for steady flow, now we are taking like special cases one by one. Okay. Initially, we taken one special case in viscid fluid. Now we are taking another special case that it is that the flow is steady. Fluid steady means that I mean flow is steady. So flow is in
Velocity should not change.
yes. So fluid is like halt or snapshot. Okay, if you think as a snapshot, so that is a steady flow. So where the partial, remember this is the partial derivative. Okay, this is not a total derivative. So fluid may itself be, if it is rotating somewhat, it is moving. So it can be still like that. But we are in the fluid frame. Okay, because position is fixed, na. Position is fixed. Only time. About time we are seeing, na? You understand, na? The two difference. Hmm? Like it's the same as it's the same as for partial and total derivative. What a total
Mhm.
derivative means? That a total derivative, total change, irrespective or where in the frame we are. But partial means it only the partial change in time, not the position. Okay.
Mhm. Right, right, right.
So yeah, it is in there. That's why it's called Eulerian. You remember that the another one is called what Lagrangian. No?
Lagrangian, yeah. Mm.
I think we will deal with Lagrangian also. So for now, this Eulerian frame. So for steady flow, del
Mhm.
delta is zero. So this term vanishes. And what did we get? So yeah, this is the yeah, we have broken down it. It's just again another vector calculation. Okay. And if you just cut it, if you divide by row, the grad p by rho will come and this row will vanish. And g, g is the uh, gravitational acceleration. Okay.
Yeah, it
That
will
is,
also have some sort of gradient.
yeah. Basically the force gradient.
Mhm.
Okay. Force
Mhm.
gradient is the per unit mass. Okay. Per unit mass. It's something. Grad phi is also potential per unit mass kind of thing. So then u dot grad u, we can break it like that. You can do by yourself like ux del x, ui del y, uz del z, operating on ux, ui, uz. So you'll have to ux del x of ux, right? So ux square by 2, that will give you the same thing, right? Ux del x of ux, right? Then if you
Mhm.
just break this one, so what will happen? Or for only ux, suppose there is only ux there. So del x of ux square by 2. So what will be? 2ux, I mean, right?
Yeah,
2ux,
that will cancel, yeah.
yeah, 2ux of del x, 2 cancel out. So ux del x of ux, so that's the same thing. And but then
Mhm.
another term will come like this. The curl term will also come minus u curl, sorry, u cross curl of u. But you can take backward also. It's just the vector manipulation. I'm not going into detail. You should try to just you understand how it is done, but you should like do it in a pen and paper, so it will give you much you
Yes,
know
yes, yes.
good satisfaction. So again, we come this term e cross curl of u, and then curl of u is right because we are taken that no, we are taken yeah we are taken implicit, so curl of u is 0. So right, curl of u 0 because we are taking for implicit written here implicit plus steady flow. So then only u square by 2. See here grad is there. So grad of u square by 2, grad of p by rho, grad of phi. So all grad will be like
When we
not grad.
integrate it, so good.
Yeah, not particular grad, but okay. How should I say? Like del. Okay, if you like this term is different. See, this term is not written like that because it is not grad p. It is grad p by rho, right? So you will have to like integrate of like basically we are integrating. Na grad is derivative, so we're integrating. Integrating this, we are getting u square by 2. Integrating this, we are getting phi. Integrating this, we will get dp by rho. Integration of dp by rho is constant. Because you remember we haven't tell yet about the row whether it is constant or not. Not yet. If it is constant, so then you can easily take it out. It will just be p by rho,
Mhm.
right? But still it is not constant.
Mhm.
Okay. So this is the famously called Bernoulli equation.
Yes, yes.
Yeah. This is the Bernoulli equation. Uh, it is heavily dealt in engineering. The all I think you have seen their uh, projects where they use the water is flowing and automatically it is filled and again automatic those kind of projects. So yeah,
Mhm.
so it's all the use of Bernoulli's equation. We have also come up to this in our school days also. right?
I guess, yes.
Yeah. So this is the Bernoulli equation in general. I think we have seen another form, the p by rho form. That is basically when the rho is constant. Okay, when the density is constant. Otherwise, okay. So
Mhm.
now, yeah, it was zero that side, and if you integrate the zero, so it will get constant. Okay, because derivative of constant is zero. So this is getting constant. This is the Bernoulli. So again, this is zero. Sorry, this is steady flow. This is zero viscosity fluid. Is it incompressible? So what will happen for incompressible? The rho will get constant, right?
Exactly, exactly. Then we
Then it
will
will be p by rho.
take
Yeah,
that prevail. Right, right.
yeah. But you can anyway. You can write integral for integration of dp by rho. It will just make your work little hard to integrate this. But there are other terms also. I think it is not included here. Like what it is called? It is called barometric fluid. Okay, barometric fluid is where we consider the pressure is a function
Function
of,
of the density. Mhm.
yeah, you know then. Okay,
Yeah, I learned that from the lectures themselves.
okay, good. Actually, in the lecture.
Mhm.
Sorry, yeah, yeah, obviously. So yeah, so for the barometric when the pressure is a function of density, so then you can, like, you can integrate over the density, and yeah, that will, I
Mhm.
think, then we will come across. Is that in the today or no? That is not in this session. Maybe question can be there, but yeah. So these are just a recap. This is for next day. Next day, I will again show the recap. That what we will get. We get the Euler equation, right? Del U del 2 plus U dot grad U of minus 1 by rho grad P
Mhm.
minus this and huge. So this is from the lecture itself. Del U del T. This is this. Take the call. This is the, this is no. This is the vorticity omega. Omega is curl of U.
Mhm.
Yeah. I think this is acha. This is a recap, and you have to show this, so you can try. Okay, sorry. Yeah. Barotropic fluid is mentioned there. Okay. Yeah, it is. It has several names because this rho is again the form, the gamma is again connected to the degree of freedom and its adiabatic index. So it has several names. Barotropic, barometric origin. So if P is equal to this, then the vorticity equation becomes simpler. Yeah, I think. Okay, this I'll talk about next session. So, can you do quickly the sample assignment file? Do we have still have time? I think, yeah, we still have. Uh, I think we still have half an hour. So, hmm, I haven't shared the previous week's presentation slide. I will. Uh, let me. I think I will share by today.
That would be helpful. Yeah.
Yes.
There's a lot.
So, yeah. Should we think should we be able to do the sample problems, or like you want to recap again on the things?
No, I think it should be fine. Considering the time foundation too, it should be fine.
Okay, on thing. Wait, let me try recap on the, yeah, vorticity. I think I haven't talked about anything on the vorticity. Okay, if I say about what physically vorticity is, So fluid is rotating, right? So you see the mm, what is called funnel, funnel flow, okay? Or when a storm is flowing, okay, you see there is a like inclination of intense like wind, even for slower wind. So there is a like intense this curly eddy kind of wind. So that is where the vorticity comes into play. So that's why we define as curl of the u as omega vorticity. So that's why it comes relevant and important. Okay. Other thing is okay. Yeah, then I think we can try to see how many this can be done. So question number one. Okay. So it is saying that consider a fluid flowing through a smooth pipe. The velocity of the fluid as observed from the lab frame is u. Okay. Fluid as observed from the lab frame. Assume that it is possible to define 2D scalar function psi x. So this is basically again the I think, stream function such that u is the curl of psi. Okay. So it's a stream function. It just didn't say directly stream function because we have to check whether you remember the term stream function or not. Wait.
Yeah, so it looks like, I mean, option A should not be correct. They have not mentioned anything about incompressibility or so. B and D seem to be the viable ones.
Which one B?
B and D.
What is the option B? A Lagrangian observer did things in fluid density. Uh, observer did things, related changes. Lagrangian observer. Okay. At the velocity of the fluid. Lab frame is U. Okay. Remember this thing. Velocity of the fluid is observed from the lab frame. Okay.
Mm-hmm.
The lab frame is U. We are not talking about the Eulerian treatment where we are ourselves with the fluid. With uh, looking from the lab frame. Okay. And the lab frame velocity is U. So there is no compressibility then. Okay. Understand? There is no compressibility then. Because you are from our perspective, from the lab perspective, the velocity is U. So you see the fluid is moving with us. So actually, yeah, no. So because it is from our lab frame, so it is not right. The Lagrangian observer. Okay. If you remember correctly, Lagrangian observer where the total derivative is constant, right? ddt. So the if it is incompressible, so del dot u is 0. Okay. And if it is incompressible, so it can't be option B because uh, yeah, it can't be there can't be compressions or rarefactions. Okay. So actually option A is correct. Okay.
Okay. Okay.
Are you okay?
Yeah. Okay.
Yeah. So option C cannot be correct because obviously streamlines can't intersect each other. Okay. Yeah, we already parallel to each other. So it's actually option A and D. Okay, I have mentioned in the next slide. Okay. See, so yeah, this is the stream function. Okay. Del dot U is 0. Yeah, it's, why it is 0 we did not mention. Obviously, it should be incompressible. Okay. Or if you do like del dot U, so you'll get that,
Oh, yeah. Mm-hmm.
right? Because now it is given 2D. Yeah. So if it is 0, so B can't be true.
Okay. Okay. Yeah. I just forgot that. Got it.
Yeah, yeah. So it's okay.
Right, right.
Yeah. Then you can move on to the next question.
But there's no information.
Oh, I think I haven't explained. I have some other slides also where I will explain the Boyson approximation it is related to.
Yeah, but as far as I can remember, it was covered in the lectures.
Uh,
And
okay, then you should be able to answer mass. No, mass energy you have already. Where one can neglect the density variation. Hmm.
yeah,
In
option
this,
C.
yeah, yeah, talk.
Yeah, I was just saying that option C is certainly correct, and there was another option. I mean, there were two approximations, two assumptions. The option C is correct, and the other one I can't remember. Maybe D, maybe incompressibility.
Yeah, I mean, these other are not approximation, right? They are conservation laws.
Yeah.
So yeah, incompressibility. So if you see the derivation, so I haven't written the derivation here. In the lecture, you can find the derivation. So you'll see that these two constants are there. Rho g term
Yes.
because the gravity term. Okay, we see that the gravity term we neglect because also there are several regions and yeah, we'll do like parallel counter treatment and incompressibility is there. Yeah, C and D are the correct answer. So then, if we head on to the third questions, pick the treatments statement that are true. Wow. Potential flows are irrotational. Yeah. And viscous flows can be described using a scalar velocity potential.
B has to be false. A is true, and the smooth because in different fluid will be
Why B
no.
is false?
B is false because viscous flows imply rotationality, and if it is rotational, then the curl of velocity wouldn't be zero, and it wouldn't have a scalar potential.
Wait. If it is viscous, there should be rotation, you are saying.
Yes.
Yeah, so if there is rotation, so
Then
then,
the curl of velocity would not be zero, and we would not be able to define a potential.
yeah, so yeah, you are saying it is wrong. But remember the thing that we said that inviscid flows are what? What are the statement again? Sorry, I need to.
Irrotational, I guess.
Yeah. I mean, correct statement.
Mhm.
Next, the vice versa. This one. Irrotational flow means inviscid flow. Okay. But does inviscid flow means irrotational? So not necessarily true. Okay.
Mhm.
So now it is a viscid flow. So should it be rotational? That is the question.
Yeah, if it is viscid, then naturally it has rotationality to it. Isn't
And naturally, but yeah, that's the thing. Now, just remember there can be viscosity, but not rotation, right? Yeah, there can be viscosity, but not rotation. Suppose that there is a viscosity, but remember viscosity and vorticity they are different. Vorticity means there has been some rotation, but this is viscosity. So fluid moving in parallel direction. Okay, there can be there can be situation, not exact, not ideally, that it can be irrotational also. And if it is irrotational, then we can define its related potential, right? Obviously, it is wrong here, but I am just in general it has like rotation. Nothing at all about this, but just be little
Yeah,
open. Yeah. potential flows, and you're saying option A is correct.
Potential flows are irrotational. I mean, again, if we are to consider all the possibilities, then we may take other causes of rotation. But if we ignore other causes, then potential flows would be irrotational.
But it is potential flow. So obviously, if we are defining the potential, so it has to be rotational,
Yeah.
right?
Right,
Yeah,
right.
that there is the nuances, no? I mean, it's like uh, if you have the potential, so that means the curl is zero, right?
Exactly.
That means irrotational. So if you have the potential,
Hmm.
then irrotational. Okay.
Right, right,
Suppose
right.
it's a different thing. Suppose there is a viscosity, but not rotation. Okay. So then it is irrotational. So there can be uh, scalar velocity potentials, right? So yeah. So A is correct, obviously. And what about C? A smooth sphere moving through a perfectly invested flow will feel no drag.
Yeah, it looks correct because the only reason for drag is just viscosity or friction.
Yes, yes, yes. Yes, so it is correct. You get it right. So option A and C are correct. Okay. So next question. Consider a steady irrotational flow of an incompressible fluid. Flow of an incompressible fluid. There are no external forces acting on this system. Steady rotational flow of an incompressible fluid. There are no external forces acting on this system. So what it is? One can define a velocity potential for this system. One cannot define a stream function. Del dot u. C certainly be zero. You can tell by just the expression, right? It is written like that. So two of the off diagonal terms of pressure tensor are non-zero. So off diagonal terms, two of the off diagonal terms. So yeah, it is correct. You can say like this. Obviously, it will be false. It is try to check your tensor abilities, but I don't know how much tensor is. So I am just giving out the answer. So yeah, it must be wrong. So steady flow, irrotational flow. Okay. So can we define the velocity potential?
Yes, obviously.
Obviously, we can. One
Mm,
cannot define a stream function. It's wrong. We can define the stream
we
function, right?
can, yeah, A and C should be the answer.
No, only A, only A. C is not the answer
Only a,
because C, why C is not the answer? Because this is not del dot u. This is del dot u, right?
oh, it's a tensor. Okay.
It itself is a, I won't say wrong. It is more like tensor. Okay. Now, if you multiply, this is a direct multiplication of two vectors. Na? This is actually, what have you learned? That vector can be multiplied by dot product or cross product, right? This is a direct product. See, this is a direct product. So it
Right.
will actually give tensor. Okay. So we don't know. I mean, I also don't know how what is the form of this tensor, but the chance of it to be zero is very less because del dot u is already zero, so del dot u may not be zero. These are the all the compartmental function. Okay, u x u y though all are get mixed up.
Mm.
Those don't be zero. So only yeah. And then I think it's the last one. Yeah, yeah. So the Bernoulli parameter is u square by 2 plus, yeah. So the Bernoulli parameter. It's called parameter. Why? Because it's not the equation, right? The equation is right hand side is constant. But the parameter itself
Mm.
is a this one, this whole thing. Why the parameters carry their usual meanings? Pick the correct statements. Tell me which one should be correct.
D is not correct for sure. And among ABC, I mean, in option A, they are saying del dot U is zero, and that directly implies option B. If option B is true,
Hello?
option yeah, if option B is true, if option then option A has to be true or not. It has to be.
Remember, we haven't yet considered about compressibility or incompressibility.
Hmm, 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 hmm.
The one only thing is like valid for in general. So, but in general, it may not be incompressible, right?
Yeah.
Conjugate means constant. So it is constant. So it doesn't matter whether del dot u zero or not. So option A is not right.
Hmm, hmm,
Option B is again conjugate where phi is the velocity potential. Again the same thing, right? Del square phi is the what Laplacian, na?
hmm, hmm,
Laplace
hmm.
equation that requires curl of u is zero and rho is constant. Again, that may not be the case because you haven't dealt that.
Only C is correct.
Bernoulli parameter is conjugate only phi is yeah. If phi is a conservative potential, right? Acha, it is written that phi is the velocity. Okay, the phi the velocity. Okay, this is different. Okay, this is the phi. Okay, sorry. Remember, this is the small phi. This is for the velocity defined. This is the gravity
Hmm.
potential.
Yeah, yeah, yeah.
So yeah, obviously
Exactly.
gravity should be a conservative in this case because if you remember, we have taken that na grad of that as phi
Hmm.
for the surface force. So sorry for the body force. So yeah, option
Hmm.
C is correct only.
Right, right.
Yeah. Okay. There is explanation. Okay. Conjugate for compressible flows as well. So in zero again boundary parameter is conjugate for compressible flows. The Laplacian of the velocity potential is zero only for incompressible. Yeah. So boundary parameter is conjugate only for steady flow. So D is also wrong. Okay. So yeah, these are the things. So I think we have solved these are the assignment question, no?
Hmm.
So hmm. So we only have 10 minutes now. I think we'll do the assignment question next time. It will take another some time.
Yeah,
I'm
I
not
guess the
able.
time is already quite ultimately.
Yeah. It's also late for you. Good.
It's fine.
Thank you, bro. Thank you for bearing with this. That has been a great help.
It's fine. It's fine. I mean, I understand it, and just hope from the next time it should be on the proper time.
Yeah. So actually, I joined through the my personal email ID. So I have been able to join to the meeting. Okay,
Okay. Okay.
not a problem. But again, I'll do another thing. Now I have signed out. Let me see if I can join. Just sign out. Internet. See, even with the sorry. Even with the signed out version, I can be able to join. So I think joining is not a problem then, huh? You also try to do like from any browser or anything, just with the meeting link, try to join.
Yeah,
I think
exactly.
I think you will be able to join. Hmm?
Mm-hmm.
You see here, you can see like different name and all, unverified, but still be directly join. I don't need to give even permission because I have removed the
Hmm.
permission.
Exactly.
So just do for, I mean, this time you because you have the team access, so you have joined. But try to like from any browser or any other device. I think it should be. Ocha, one thing need to be checked that
It's
whether it
9
can be
o'clock.
accessed from the web browser.
Yeah, yeah. From the web browser, it was very much accessible. I joined on the first day using that only.
Okay. So app is also accessible because now I just joined through the app. I think the
Yeah,
problem is solved. Only thing is I think students are not
might be.
maybe with the thought that it is not working.
Maybe. All
Because
right,
in the
then.
teams I also see. Hmm?
Yeah, I was saying exactly might be the issue. And all right, then I guess see you in the next Saturday.
Yeah, yeah.
Mm,
Stop sharing. Yes. Okay.
okay.
Yes, bro. Okay. Thank you. Good
Thank you.
night.
Good night.
Hmm. So I think people can join. Not directly. I think the problem this issue is solved now. You'll be able to join. Okay. Okay. So next time we'll do the more assignment problems and some basic things about these other functions. But please, I will request you all to okay, request you all to join the live session. It will be much helpful for you as well as me because it will be a um, intuitive session for both of us. Otherwise, it will just like counterintuitive. So yeah, so please join. So next week we will do the problems, assignment problems. Yeah. Thank you. Good night. Yeah, you can and okay. For you, I'll also give that. Yeah, you can join my. I think I'll share my channel link. You can join my channel. Okay, this channel. I'll share the link to you. It's a big link. So yes, you're able to join. And next day we'll start from here or things that what we have discussed so far. All the questions and things. Okay, this will be the recap. and we'll do the more problems, some problems. Okay, so yeah, that's it. Thank you. Thank you, Sahil, also, and Varun. I've joined the sessions. Thank you. Okay, so that's all. Thank you. Thank you, everyone. So yeah, you can leave. So, good night. Let's start our session. Yeah. Okay, good night. Sabak here. Um, I've recorded the session, so I'll join the stop recording function.